Hello everyone, welcome to my YouTube channel. In my last video, I have discussed about the definition of symmetric and skew symmetric matrices. Today I will discuss some important points related to the symmetric and skew symmetric matrices. So let's start with the first point, and that is as follows. A transpose and A transpose A are symmetric matrices. In order to prove that they are symmetric matrices, let's assume it equal to a new matrix B equals to A transpose A. In order to show that A transpose and A transpose A are symmetric matrices, we have to take the transpose on both sides. So, taking transpose on both sides, we have A transpose A whole transpose. Now, transpose will distribute over each matrix. So this becomes B transpose equals to A transpose into A transpose. Now A transpose whole transpose becomes A only, and this is A transpose. So B transpose is also equals to A transpose. So from here we can write that B transpose is equal to B. This implies B is a symmetric matrix and B was equals to A transpose A. So A transpose A is a symmetric matrix. Similarly, you can show that A transpose A is also a symmetric matrix. Now, the second point says that A is symmetric. This implies every integral power of A is symmetric for K belongs to Z. That is, if you have a matrix which is symmetric, then integral power of that matrix will always be symmetric for K belongs to Z. So let's have one example. I am proving it by taking a counter. I have a matrix A, a 2 cross 2 matrix. I am taking 1, 3, 2, 2. This matrix is a symmetric matrix. So if we find the value of A square, this is the integral power of A. So if it is symmetric, then we can say that our second statement also holds. So let's multiply the given matrix with the same matrix. After taking multiplication, we get that 5, 8, 8, 3. Again, this is a symmetric matrix. So we can say from here that if A is symmetric, then every integral power of the symmetric matrix is again symmetric. Now we will prove the third property. So this is just a statement, remember it. If A and B are symmetric matrices of same order, then AB is symmetric. Suppose you have two symmetric matrices which have same order, then you will say that the product of that two matrices is also symmetric if and only if they commute with each other. That is, AB is equals to BA. If this condition holds, then AB will be symmetric, and it is given that A and B are the symmetric matrices of same order. And if these conditions are given, then AB must be equals to BA. So this was the property number 3. Now the last one, if A is symmetric and determinant of A is not equal to 0, then adjoint of A is also symmetric. The proof of this property is your homework. You can try it by yourself. You just take a symmetric matrix whose determinant is not equal to 0, that is an invertible matrix, and then find its adjoint by taking cofactors matrix, and then you will get that the matrix that you find is also a symmetric matrix. So let's discuss about the properties of skew symmetric matrices. So by the definition of skew symmetric matrices, we know that A transpose is equals to minus A, and if you want to apply it on each entry of A, then you can write it Aij. By taking transpose, the row become column and column become row. So Aij becomes Aji, and since A transpose is equals to minus A, so we use a negative sign. And this is true for all I, j. Now if we talk about the diagonal entries, so we know that on diagonal I becomes j, that is Ai. This type of elements are obtained. So on diagonal, for diagonal entries, we have AII, that is first row, first column, second row, second column. We are talking about that type of elements which are on leading diagonal. So AII becomes minus AII. Now if we take this minus AI on that side, this becomes AII plus AII is equals to 0. Now 2AII equals to 0 implies AII equal to 0. This implies what? These are the diagonal entries. This implies that for a skew symmetric matrix, the diagonal entries will always be 0. That is, all the diagonal entries of a skew symmetric matrix is 0. If A is skew symmetric, then A minus A transpose is always skew symmetric. Let's consider B equal to A minus A transpose. Now, B transpose, because we need to determine that this is skew symmetric or not, so we will take B transpose. So this becomes A minus A transpose whole transpose. Now transpose distribute over A and A transpose, so this becomes A transpose minus A transpose whole transpose. Now we know that A transpose whole transpose is equals to A, so this becomes A transpose minus A. We can write it as, if we take A as common, this is equals to minus A transpose. So this is equals to what? Minus B. This implies that B transpose is equals to minus B. This implies B is skew symmetric matrix, implies A minus A transpose is skew symmetric matrix. Now the next property is, if A is skew symmetric matrix, then the scalar multiple, where K is any scalar, the scalar multiple of a skew symmetric matrix is also a skew symmetric matrix, where K is a scalar. K is a scalar. So this property you can prove by yourself. Just consider a skew symmetric matrix whose diagonal elements are 0. Then Ka, and take any scalar K and multiply it with a given skew symmetric matrix. You will get that the matrix that is obtained will be a skew symmetric matrix. Now the next property is, if A and B are skew symmetric matrices, then AB is skew symmetric. This product of the two skew symmetric matrices will be skew symmetric if and only if AB equal to minus BA. That is, AB plus BA equals to 0. Now I am going to discuss the definition of Hermitian and skew Hermitian matrix. The definition of Hermitian matrix is as follows. A square matrix A is equals to Aij is said to be a Hermitian matrix if conjugated transpose of A is equals to A. That is, A equals to A conjugate. Firstly we take the conjugate and then its transpose. So if conjugated transpose of A is equals to the given matrix A, we call that the matrix is Hermitian matrix. In this case, the matrix can be of complex entries, so that's why we take the conjugate, then imaginary value will becomes negative after taking the conjugate, and if it is positive it becomes negative. That is, if we write in terms of element, this becomes Aij is equal to Aji. After taking transpose it becomes Ji. Row becomes column and column becomes row, and we take its conjugate. And this is true for all I, j. Now if we talk about the diagonal entries of a Hermitian matrix, so for diagonal entries, for diagonal entries we have Aii is equals to Aii bar. This means that the conjugate of the element is equals to the element, and this is possible only when we take a real number as the diagonal element, because the conjugate of a real number is the number itself. So diagonal entries of a Hermitian matrix must be real. So AII is real for all I. So every diagonal element of a Hermitian matrix must be real. Now we know that in order to say that, or we say for Hermitian matrix, the conjugated transpose of A is equals to the matrix. Some books denote it by A star. The conjugated transpose of A is denoted by A star, and some books denote it as A theta. So whichever notation is given, you will understand that it is a Hermitian matrix. Now let's have some example. The first example that I have taken is a 2 cross 2 matrix. The elements of this matrix are 1, 1 plus I, 1 minus I, comma, and 2. Now, in order to prove that it is a Hermitian matrix, firstly we take the conjugate of this matrix. When we will take the conjugate, the real terms become same, but the complex terms becomes positive. If they positive, they becomes negative, and if they are negative, they becomes positive, and only imaginary parts. That is, the conjugate of 1 is 1 because it is a real number, but the conjugate of 1 plus I becomes 1 minus I. We will discuss it in the complex analysis. Now 1 minus I, the complex of these terms becomes 1 plus I, and this is a real number, so its conjugate will be the number itself. So the conjugate is as follows. Now we have to take the transpose, because we have learned that if the conjugated transpose of A is equals to A, then we say that A is Hermitian matrix. So let's take transpose. If we take the transpose of this matrix, the rows becomes columns, that is 1, 1 minus iota, and this becomes second row becomes second column, so this becomes 1 plus iota into 2. Now if you compare the given matrix by this matrix, they are equal, that is A is equals to A star or A theta or the conjugated transpose of A. So from here we can conclude that the matrix that we have taken is a Hermitian matrix. Hermitian matrix. Now we will discuss about the definition of skew Hermitian matrices. So the definition of skew Hermitian matrix is as follows. A square matrix A is equals to Aij is said to be skew Hermitian if the conjugated transpose of the matrix A is equals to the negative of the matrix A. If we want to write this statement in form of entries, then we say that Aij is equals to, firstly we interchange the rows and columns, so this becomes Aji. Now we take the conjugate of this term and this becomes the negative, so we take negative sign as well. That is, the negative of conjugated transpose of A is equals to the matrix A, and this is true for all I, j. Now if we discuss about the diagonal entries of skew Hermitian matrix, so for diagonal entries I becomes j, or I is equal to j. So for diagonal entries we have Aii is equals to negative of Aii bar. Now we know that Hermitian and skew Hermitian matrix contains complex entries. So if I consider it as a complex number, that is A plus IB, that will be equals to minus of conjugate of A plus IB. And we know that after taking the conjugate, this becomes A plus IB equal to minus of A minus IB, because we are taking the conjugate of complex terms. So I becomes minus I, and this becomes like A minus IB. Now if I distribute negative over these elements, this becomes minus A plus IB. This is plus. So iota b cancelled out, and from here we get A plus A equal to 0. This implies A equal to 0. Now the A was the real part of the complex number. So from here we get that on the diagonal entries, the real part of complex number becomes 0. That is, the diagonal entries of a skew Hermitian matrix are always imaginary, or purely imaginary we should say, because only iota b terms is left, and that is a purely imaginary number. It may be 0 also, because if you take b as 0, then iota doesn't matter. So the diagonal entries may be 0 also. So in a skew symmetric matrix, the diagonal entries are either purely imaginary or 0. Now let's have some example of skew Hermitian matrix. Sorry, I should write here skew Hermitian. Skew Hermitian. So the matrix is as follows: 2 iota, 1 plus iota, 2, minus 1 plus iota, 0, 3 iota, 3 iota, minus 2, and here we are taking 3i. Now if we see, the diagonal entries of this matrix are purely imaginary, or it is 0. So this type of matrix we have to take. Now firstly we find the A transpose. The order may be anything. Firstly, or either you can take first transpose or you can take the conjugate. The answer will be same in each case. So if we take A transpose, the rows becomes column. So first row become first column, 2i, 1 plus I, and 2. And this second row becomes second column, minus 1 plus I, 0, 3i. And the third row becomes third column. So this becomes minus 2, 3i, 3i. Now we will take the conjugate. If we take the conjugate, the matrix becomes 2 iota becomes minus 2 iota, because we replace I by minus I in each case. So minus 1 minus I, minus 2, 1 minus I, 0, 3i, 2, minus 3i, minus 3i. This is also minus 3i. Now if we take negative outside from this matrix, this can be expressed like this. This becomes 2 iota, 1 plus iota, plus 2, and iota minus 1, 0, 3 iota, 2, 3 iota, 3 iota. Now if you compare A with this matrix, A is equals to this matrix. So from here we can write that the conjugated transpose of the matrix A is equals to minus of A, and this implies that A is skew Hermitian. A is skew Hermitian matrix. So I hope the definition of the Hermitian and the skew Hermitian matrix is clear to all of you. In my next session, I will discuss some important points related to these matrices, and I will discuss some more matrices which are left, like nilpotent matrix, involutory, idempotent, this type of matrices. So till then, bye bye. Thank you. If you are liking my content, please subscribe my channel.